Okay, yeah. Chapter 3, Section 1, number 7. When air expands adiabatically without gaining or losing heat, the pressure and the volume are related by this formula, where C is a constant. Suppose that at a certain instant the volume is this, so that's a changing number. The pressure is this, and is decreasing at a rate of the pressure is, so this is a change in the pressures, P, V, P, T. Excuse me. D pressure. Change in the pressure with the change in time. Sorry, not messing up. Okay, so we need to go back to this formula and take the derivative with respect to time. So the derivative of P with respect to time is dP dt. And this is a product unless we divide by, let's divide by V to the 1.4. So let's start this formula with P equals C V to the negative 1.4. So this is a constant times it, so I don't have to do product rule. Otherwise, I'd have to do product rule here. So the derivative of pressure with respect to time is equal to a constant times the derivative of the volume with respect to time. So the derivative of this is going to be negative 1.4 V to 1 less than that, negative 2.4. And this was V, not T, so dV dt. The 11 is dP dt. At what rate in cubic centimeters per minute is the volume increasing? So they want us to find this. So we need to plug in 550 in for the volume at that instant. And the pressure was 77. So we're going to use this to figure out what the C was. So the pressure was 77 equals times V to the 1.4 equals the constant, and the volume was 550. So I need my calculator here and figure out what C is. And the calculator says 77 times 550 to the 1.4 gives me a C, a really big number for C. C is equal to 528,443. So that would be here, and it would also fit into here, where we have the rate of change in the pressure is this. So we're going to put in this number here, negative 1.4 V to the negative 2.4. Figure out this number and divide it into this to figure out how fast the volume is changing. So C, I have it in here, times negative 1.4, parentheses, the volume at 550, to the negative 2.4. I lost my times. So I've got C times negative 1.4 times 550 to the negative 2.4, enter. And that's what I got to divide into the change in the pressure with the change in time, which they told us was 11. So I got to take 11 and divide it by this answer, and I get 56.12. Negative 56.12. And this would be, we're doing the change in pressure, so this is kilopascals per, what rate is the volume? What rate is the volume changing? Oop, I messed up here. Sorry. 11 goes here. We have to divide it by C in this. Okay, I did that wrong. So going back here, we have this times negative 1.4 times a volume to this power. This number has to divide into dPdt. So get this, and then I divide it into 11, and that is the right answer. Got to make sure I'm doing this right. Negative 56.122 is the change in the volume in cubic centimeters per minute. So the pressure, if the pressure is decreasing, wait a minute. I should have put a negative in for the 11 because it's decreasing, so that makes this plus. So if the pressure is decreasing, the volume should be increasing. So that should be the answer. Sorry I made so many mistakes getting there. Okay. Water's leaking out of a inverted conical tank. That's one that's on its nose. So it's dripping out pretty fast at 12500 centimeters cube per minute. At the same time, the water is being pumped into the tank at a constant rate. So there's water going in. The tank has a height of 13. It has a diameter of the top, so the radius of the top is half a 7, 3.5, and these are both in meters. If the water level is rising so the change in height with respect to time is rising at 15 centimeters per minute. Notice I was watching the units again. When the height is 4.5 meters. So it's part way up. So it's rising, it'll be rising faster here and slower as it goes. So a cone. Let's put a coordinate system on it. And the way the classes have been going here, you guys like to put the x-axis here and the y going up. So I will do that. So the volume of a cone is 1/3 pi radius squared times the height. Now, we're going to be looking at the volume here, not the whole cone at some point down here. So the radius is going to be different here, and the height is going to be different here. But we know that this triangle is similar to this triangle. This is a similar triangle one. So if I call this height H and radius R, let's see, what do I want to do? I've got to get how the height is changing, so I want to get rid of R. So I'm going to start with R in my numerator, H in my denominator. R to H is in the same ratio as 3.5 is to 13. Because this triangle is similar to this one. The cones are all proportional. So, I need to get the R out of here. So R is equal to, if I multiply both sides by H, R is equal to, to that. So the volume is equal to 1/3 pi. And I got to square this constant, so it's going to be 3.5 squared over 13 squared, h squared times another h, so that's h to the third. Now I have what I needed to do. When you're doing a problem like this, you need to relate the volume to the height, because they want to know how high the water is. If the water level is rising, so that's dH dt, when the water is this, then you need to relate that to the volume of water going in and out. So we're going to take the derivative here. All of this is a constant. So this is going to be dV as time changes equals whatever this number. Let's figure this number out. Pi divided by 3 times 3.5 squared divided by 13 squared. It's 0.0759. 0.0759. So dV equals 0.0759 times 3h squared dH dt. Off the page there for you. Let's adjust the camera a little bit. Okay. And then they told me that the water is leaking at that rate. So, and there's water being pumped in, and that's what we're supposed to be finding. So dV dt has two parts. The rate at which it's going in, dV dt going in, minus the dV dt going out, which is 12500, equals this constant 0.0759 times 3h squared, and they said when the height is 4.5 squared dH dt, and they said the height was changing at 15 centimeters per minute. So I've got to figure this number out, add 12500 to figure out how fast the water's going in. The water going in minus how much is leaking is what's causing it to rise. So we've got my number that I have here times 3 times 4.5 squared times 15 and then I've got to add to this. That's how fast how much volume is going in to keep it rising, and this is leaking, so we got to go plus 12500, and so I didn't do plus. So 69 plus 125 is 125. 120. Oh, this is in meters. This is in meters. This is in meters. This was in centimeters. And this was in centimeters, cubic centimeters. So I need to do some conversions here that I forgot to do. So we need to be in meters, or change these to centimeters. It takes a centimeter by a centimeter into meters. There's 10 centimeters, 100 centimeters across, 100 centimeters back, 100 centimeters. That's a million. It takes a million of these to make 1 cubic meter, so I have to divide this by 1 million. To get that unit right. That would be in meters cubed. And then all these other ones are fine except this one, centimeters. I need to divide it by 100 because there's 100 centimeters in a meter. So this 15 should have been something different here. So we're going to do this again. We have these were all meters. I just needed to change the height. No, the height was in meters, so that's 4.5, so that stays the same. So it's just the 15. So the 15 has to be divided by 100, so it's 0.15. Let's see. Clear. 0.0759 times 3 times 4.5 squared times 0.15 meters, and that's how many cubic meters are it takes to raise the water. Now, there's a leak here, and we need to find out how many cubic meters are leaking here, that it's going to have to add to this, that the water's going to have to be putting in to be going over. So we're going to add to this 12,500, but we need that in meters cubed, so I'm going to divide by 1 million. And so the water going in is that many meters cubed per minute, but they want it in centimeters cubed per minute. So if that's that many meters cubed, we have to multiply that by 1 million to find out how many centimeters cubed per minute need to be pumped in. And that's 704,139 centimeters cubed per minute. Okay?